Hello and welcome, everyone. My name is Dane Menke. I am the Digital Marketing Manager here at Regenesis in Land Science. Before we get started, I have just a few administrative items to cover. Since we're trying to keep this under an hour, today's presentation will be conducted with the audience audio settings on mute. This will minimize unwanted background noise from the large number of participants joining us today. If the webinar or audio quality degrades, please try refreshing your browser. If that does not fix the issue, please disconnect and repeat the original login steps to rejoin the webcast. If you have a question, we encourage you to ask it using the question feature located on the webinar panel. We'll collect your questions and do our best to answer them at the end of the presentation. If we don't address your question within the time permitting, we'll make an effort to follow up with you after the webinar. We are recording this webinar, and a link to the recording will be emailed to you once it is available. In order to continue to sponsor events that are of value and worthy of your time, we will be sending out a brief survey following the webinar to get your feedback. Today's presentation will discuss the need for sustainable PFAS remediation, comparing the environmental impact of in situ sequestration to pump and treat. With that, I'd like to introduce our presenters for today. We're pleased to have with us Jarno Leitinen, Head of the Department for Climate and Circular Economy at Ramboll. Jarno Leitinen currently works with topics related to resource management and climate impacts. In his various roles at Ramboll, Jarno has acted as the head of sustainability, led global sustainable remediation programs, and promoted leadership in sustainability through various projects, publications, and speeches. We're also pleased to have with us today Gareth Leonard, Managing Director of Regenesis in Europe. In his current role, Gareth Leonard manages a dedicated team of in situ remediation specialists to provide the design and implementation of remedial solutions for environmental consultants, remediation contractors, and end users. He has worked in the remediation industry for over 20 years, having provided successful remediation designs and implementation for over 1,000 projects across Europe, the Middle East, and Africa. All right, that concludes our introduction. So now I will hand things over to Gareth Leonard to get us started.
Hello, everyone. My name is Gareth Leonard. I'm the Managing Director of Regenesis at Europe. Gives me great pleasure to be giving this presentation with Jarno. I'm going to set the scene over the next few slides, essentially, or what the issue is that we're trying to address. I'll talk about the technology that we'll be talking about today, and then introduce the site on which a life cycle analysis and sustainability study has been completed. And then I'll hand that over to Jarno, who will take you through the methodology and the results that came from that. So we're talking about the need for sustainable PFAS remediation, and we're comparing the environmental impact of in situ sequestration to pump and treat. Okay, so per and polyfluoroalkyl substances, PFAS. I want to go through on this slide, what are the attributes that make them such a problem, essentially? And the first thing is that they're just incredibly useful. So they are omniphobic, which means they're really good at waterproofing and oil proofing. So they've got all sorts of uses for coating in commercial and domestic settings. They're also good for aqueous film forming foams, which I'm sure you've seen for putting out fires. Now, this makes them a contaminant that we have actively sprayed onto the ground on thousands of sites for decades now. So there's not many other contaminants we've done that. Arguably, petrol filling stations with the filling up cars, we drip some oil, but this is very much intentionally putting this foam, this contaminant, onto the ground. So once it's on the ground, the contamination, the PFAS, sorbs to these soils, often in the upper part of the vadose zone, where it provides a reservoir of contamination for many, many decades. Now, as more foam is put on top, or rainfall enters the ground and infiltrates the vadose zone, you get leaching of this contamination. It moves vertically through the formation, and then when it touches the groundwater, PFAS is very mobile in groundwater. So it starts to move down gradient. It's recalcitrant to degradation. It doesn't really biologically degrade past a certain point. It doesn't really chemically oxidize. So it just keeps on going. And it's toxic at very low concentrations. Certainly the longer chain PFAS compounds are toxic at very low concentrations. And so what you end up with is these very large, very dilute plumes that are still driving a risk. So the result is that PFAS are essentially everywhere. This is a map from Le Monde newspaper. It's the Forever Pollution map. You can go, I've put a link at the bottom there, and you can go and have a look. It's interactive. Very interesting. So it's a number of theoretical sites with known contamination or presumptive contamination. There's also a version of this in the US. They've taken a different approach. It's in Environmental Health News, where there's about 57,000 sites they've suggested are in the US. So you're looking at tens of thousands of sites here, which is a huge amount of sites we need to clean up, which we've only just started dealing with. So if you think about all the remediation that we've done in the past and all the contaminants we're dealing with now, this is a whole extra area that we need to deal with. So how can we treat PFAS? As remediation professionals, we tend to revert to removal and destruction. So these are different approaches that you can take for that. So the treatment efficiency is on the y-axis, the higher up, the better, against contaminant concentration increasing along the x-axis. So if you were, say, treating a petrol filling station, you might have free-phase fuel. So you start with physical extraction of that. That becomes inefficient once you get rid of the easily removed floating contamination. So you move to chemical oxidation, and then you want to get to low targets. So you then move to biological degradation to get you there. Well, with PFAS, we don't think there is any biological degradation, certainly at this point. It's recalcitrant to chemical destruction as well. So you're left with physical removal of the contamination. Now, physical removal of the contamination is very effective at high concentrations, but PFAS exists in very low concentration, nanograms per liter. It's still driving a risk. Some targets are looking at picograms per liter. So the result is that it's an inefficient way of removing the contamination. You're pumping a lot of water to get a small amount of contamination. You're going through a lot of granular activated carbon. There's a lot of energy, equipment's running out, and ongoing costs. And of course, all of this has a carbon footprint. So we're looking at trying to deal with a global issue, and we're potentially going to increase our carbon footprint as an industry, as cleaning up contamination. And that might exacerbate another challenge to the globe, which of course is climate change. So how are we going to deal with one global issue without exacerbating another one? So one way we can do it is look at the sustainability of the potential remedial approaches we're considering for PFAS. So by doing a sustainability assessment, by doing a life cycle analysis of the options, it means that you're not looking at your site in isolation. You're looking at the effects of the remediation that you're doing, not just at whether it's successful, not just at whether the cost of it, but what is the wider impact on the globe of what you're doing on this site. So sustainable remediation is defined by ISO 18504 as the elimination or control of risks whilst optimizing the environmental, social, and economic value of the work. So one approach that I'm going to talk about just now is enhanced attenuation, which is able to deal with very low concentrations of PFAS and also has the potential to reduce the impacts, the carbon dioxide production, etc., that you would otherwise have from physical treatment. So enhanced attenuation of PFAS, what do I mean? PFAS doesn't biologically degrade, but of course, natural attenuation doesn't just mean biological degradation. It's also diffusion, dispersion, volatilization, sorption, and abiotic degradation. So what we want to do is take a natural attenuation attribute and enhance that. And what we're talking about today is looking at the ability of the aquifer to sorb and retard the PFAS contamination so that it increases the retention of that contamination, which enhances the attenuation of that PFAS plume. So there's a really good paper by Chuck Newell on this approach for PFAS. In that paper, they consider 7 different approaches for enhancing the attenuation of PFAS, one of which is the injection of particulate sorbents, which we're going to be talking about today. And essentially, you're putting a sorbent into the surface, you are sorbing the contamination that's moving through, you're slowing the movement of that contamination through the subsurface. And the effect is that the peak concentration that then gets to your down gradient receptor, whatever that might be, it might be a drinking water well, it might be a surface water stream, that never gets above an actionable level. So in an uncontrolled situation, you've got the contamination getting into the groundwater, it's moving down and it's discharging into your receptor at concentrations that are problematic. By putting a sorbent in, you are slowing the movement dramatically of the contamination through the subsurface so that that discharge into the receptor never gets above the unsafe level. So if we look at the remedial approach, if we consider the PFAS source plume system, what we've got here is an airport, a fire training ground on the airport. They're spraying AFFF, practicing putting out fires, etc. It's getting through the cracks, it's getting onto the grass, it's getting into the drainage system. It moves down through the vadose zone, hangs up at the capillary fringe, dissolves into the groundwater, and then you've got a plume that is then going off-site, causing off-site liability, maybe impacting the aquifer itself, getting into drinking water, surface water, etc. So the way we are considering treating it in this presentation today is using a colloidal activated carbon product. So it's a liquid version of activated carbon. So you'll have come across granular activated carbon in Brita filters at home or in pump and treat systems for treating water. That has particulate size of about 1,000 micron in diameter generally. Powdered activated carbon you might have come across, it's got a diameter of about 50 to 250 micron in scale, and that is used for vapor treatment generally. What we've done here is we've milled the powdered activated carbon down to a diameter of about 1 to 2 micron. So that's the size of a bacterium. That's about the width of a red blood cell. We've then suspended that in water, so you've got a colloidal liquid. And the idea is that you inject that in low pressure into the subsurface. It spreads through the subsurface, it coats the aquifer, and it changes the behavior of the aquifer so that it retains that contamination. So it comes in several forms. We've got source stop for source areas, plume stop for plume barriers. We've got Petrofix for petroleum hydrocarbons. So it's used in the source area in the plume. In the source area here, the first place would be targeting the soil in the vadose zone, so that upper part of the vadose zone. We'll be using the colloidal activated carbon product source stop. We'll also probably be using powdered activated carbon as well. And what we're doing here is the contamination is already sorbed to the soils. We're binding that more tightly so that we reduce the leachability of the contamination from the soils. So that prevents any further contamination coming off those soils and discharging into the groundwater. At the capillary fringe, because PFAS is surface activated, it tends to stick to the surfaces of the water where you've got a mix of air and water. So you get contamination hanging up at the capillary fringe. We can put it in a horizontal barrier at that point. It'll sorb that contamination, prevent it dissolving into the groundwater, catch any residual contamination coming from above. We can inject it into the groundwater at the head of the plume, just sorb that contamination, prevent it from migrating any further. And at that point, that might be enough. For a lot of PFAS sites, that might be all you need to do, and then you allow the enhanced attenuation of the down gradient plume to occur. If, however, you're in a sensitive area or you've got a receptor immediately adjacent to the site or a legal responsibility to prevent contamination coming from the site, you can also inject the product as a barrier at the edge of the site as well. And that allows the groundwater to move through, but prevents the contamination from moving any further. So we've used this on 41 sites so far across North America, in the UK, Scandinavia, Middle East, and Australia. We've got a lot of case studies on our websites, which we can provide, but I just wanted to reference a nice paper by Grant Carey and the University of Waterloo, where they've gone and looked at multiple sites and pulled the data together, worked out longevity. It's a good read. So there's data on 16 sites up to about 6 years. One of those sites was the inappropriate technology. That we started a pilot study essentially in an uncontrolled landfill. So the DOC was so huge, it was swamped. So we didn't take that any further. But of the other sites, we're getting about 82 to greater than 99% reduction in the PFAS concentrations, which is then maintained for a very long time. So an interesting read, that paper. So a site that we've done in the UK and one that forms the study that we're talking about today is an airport in the UK. The picture on the right I've blurred out because firefighters can recognize each other's airports by the, whatever they call it, the fake aeroplane that they put out the fires on. So you have to blur it out so they don't recognize each other's airports. But basically the light green is the airport, and you've got the groundwater flowing from top left to bottom right. The darker green in the bottom right is offsite. That's actually a hill going down to a river, and it's darker because it's got defensive planting, lots of thorny bushes all the way down that slope. And what happens is the groundwater is moving through made ground alluvium and mostly the river terrace gravels sitting on top of a London clay. As it gets to the fire training ground, the grey area there, all of the drains have got PFAS in them from the AFFF. The interceptor is leaking there as well. So the groundwater is picking up that contamination and taking it off the edge of the site. There's a spring line down the hill from the site, and PFAS is being picked up in that spring. So basically the PFAS is then impacting surface water. So it's a voluntary remediation to remove the offsite liability. They wanted us to come in and stop the contamination coming off the site. And then what's going to happen next is they're going to go in and replace all the drainage, remove the soils. We'll apply product in there as well and remove that source as well. So we've completed a plume stop barrier on the edge of this site. At the edge of this site, it's a 120-meter long barrier that basically creates this subsurface filter, prevents the PFAS from going any further. That's what it looks like in cross section. And what we did is we did the first 15 meters or so of the barrier as a pilot study. We then monitored for 9 months and showed that we got down to a almost non-detect for the PFAS. And then once we were happy that it was working, we then continued the barrier on and completed the full treatment. That was finished in February of this year, and it's continuing to work. So having done the work, we know it works, but increasingly we need to consider, which is the reason we're here talking about this today, the sustainability of these approaches. And I've done in situ remediation for a long time, so I'm biased. I look at it and I think, okay, we must be more sustainable, right? We're just coming to site for a short amount of time. We inject something in the ground and then there's no energy used, there's nothing come to the surface. It feels like we should be more sustainable, but we're at a point where we have to get better than that for all contaminants, but particularly for PFAS. How are we going to tackle all of this contamination without quantifying how sustainable our options are? So we decided to take this real site, this full-scale treatment, and do a sustainability study on it, but what we needed was professional help. And that, of course, is where Janu and Ramboll come in. So I will hand over to Janu now.
Thank you very much. My name is Jarno Laitinen. I work as head of department for circularity and climate in Ramboll here in Finland. I'm very happy to be here to talk about sustainability, and very happy that we've been able to work with Regenesis, one of the forefront companies actually supporting sustainable remediation, in understanding better where the environmental impacts on a remediation project originate and to quantify those. I'm going to present today a study on the sustainable remediation, where the aim was to compare 3 alternatives for in situ and ex situ remediation for PFAS contaminated groundwater. The case site was presented in the previous presentation, but I'll give more in-depth information into the remedial alternatives that were compared in the upcoming slides. This study was in fact complementary to previous LCA work, that life cycle assessment work that we did on Regenesis remediation products, and it's actually involving a real-life remediation site. Since the site in question is already undergoing remediation, this is a comparative assessment where we are doing this kind of a best practice designs that we are using as alternatives to compare with. And the best practice designs and remedial alternatives are pump and treat, where in the first alternative, the groundwater is filtered with normal granular activated carbon. And then the second alternative is aiming to lower the environmental footprint that comes with the use and discarding of the activated carbon by adding a separate stage of foam fractionation to the pump and treat solution. I have to highlight that the study did not focus on the remedial options appraisal or the technical efficiency of the selected methods. They were designed to fulfill the same remedial goals. And all designs for these were done at a general level. So when, for example, designing the pump and treat, we did not include all the valves and fittings and everything. So it is in that sense, not a fully complete study of everything, but at a level that gives enough data to draw conclusions upon. So to start with, what is sustainable remediation? And if we follow the ISO standard on sustainable remediation, it is defined as the elimination and/or control of any acceptable risks in a safe and timely manner, while optimizing the environmental, social, and economic value of the work. Well, what this actually means, if we think about a contaminated site remediation, I have here a simple graph showing a site where we have contamination shown on the orange line, and that causes a certain impact on the environment. Now, as we start remediating the site towards the compliance level, the contamination decreases and the impact is decreased as well. But all actions that we take on the site, they introduce impacts then on the economy, then on the environment, and also on the society. So if we sum up all the impacts from both the contamination and from the different sustainability angles and look at the sum impact, we can see that when we reach the remediation, the compliance level, we've actually reduced significant gains in our contamination, but only marginal gains in terms of sustainability. And when we talk about sustainable remediation, our aim is to find the balanced point where the benefits from the remediation are in balance with the impacts that the work have on the society, environment, and economy. But often we still tend to move towards very low threshold levels or unnecessary remediation even. And in those cases, I argue that we are actually not causing any benefits on sustainability, but in fact have negative impacts as an overall. So when we talk about sustainable remediation and think about how to measure sustainability in a project, first of all, you have to understand that when we talk about sustainable remediation, we're moving from the pure risk management and remediation perspective into a more holistic way of optimizing the environmental, social, and economic value that we gain from the project. So in terms of sustainability, it's not enough just to mitigate the negative inputs, but at the same time create some positive inputs for the community or the ecological sustainability. And there isn't really a one-stop shop for sustainability or sustainable remediation, but this needs to be determined on a case-by-case basis. And the way how you can determine sustainability, you have to have a process that's systematic, it's clearly documented, and you can clearly justify all the decisions that you've done during the process. So there are different tools that you can do to determine the sustainability. Most frequently used tools are environmental risk analysis. That is very well familiar to all of us working in environmental remediation. But other tools such that will be presented in this presentation include lifecycle assessment, lifecycle cost assessment, and multi-criteria analysis. And these different tools target different aspects of sustainability, whereas the lifecycle assessment has a very specific environmental angle, and the lifecycle cost assessment an economic angle, and the multi-criteria analysis has a more multifaceted approach, looking also to the social and other environmental aspects. So if you want to have a thorough and full view on the sustainability, you should use multiple tools in your assessment. So following that, I'm going to present you how we looked through the sustainability assessment in this specific project. I'm going to walk you through a carbon footprint assessment, a carbon handprint assessment, life cycle cost assessment, and then a multi-criteria sustainability assessment done with the Sure by Ramboll assessment tool. But to start off, I'm going to give a quick overview of the compared remediation methods. The previous presenter gave a very good overview of the first one, immobilization with colloidal activated carbon injection. This is a remediation method based on in situ sorption and retention of the contaminants. And since this approach was already applied on the site and it was based on the Regenesis product Bloom Stop, that was used as the basis for the assessment. The two alternatives, they were both based on pump and treat, which is a remediation method based on extraction of the contaminated water, sorption of the contaminants on a filter medium, and then treating that filter ex situ. In our assessment, the filtration is based on granular activated carbon, which is the most common adsorbent, and a bituminous coal-based activated carbon was used in the assessment, as that's what the majority of systems globally use. And that's also one of the better activated carbons for PFAS adsorption likewise. In the assessment, the spent activated carbon was assumed to be disposed off-site for landfilling. In the third alternative, a separate step of foam fractionation was added. And the aim of adding the foam fractionation was reduce the amount of carbon used in the filtration process. This I will show later what the quantities are that we assume for the reductions. But in addition to coal, then of course the foam fractionation produces an additional waste stream from the PFAS foam. And both the PFAS foam and spent CAC were assumed to be disposed either to thermal destruction or, in this case, landfill. First, I'm going to move you through the carbon footprint assessment. And to start off, what is a carbon footprint? It's also known as the greenhouse gas emission assessment. The aim is to evaluate the total greenhouse gas emissions and express those as carbon dioxide emissions equivalents. The greenhouse gas assessment, or the carbon footprint assessment, is a subset of life cycle assessment. The main difference here is that whereas the greenhouse gas assessment looks only to one environmental impact category, being the greenhouse gas emissions, the life cycle assessment takes into account more environmental impact assessment categories like the land use or water use, acidification and eutrophication. In addition to doing the carbon footprint assessment in this project, as I said in the beginning, this project was a follow-up on work where we also did product level life cycle assessment for Regenesis plume stop products. These results were also used in the assessment, but they're not introduced or included in this presentation. In general, a life cycle assessment or a carbon footprint assessment follows 4 stages. You first define the goal and scope of the assessment, then you do a life cycle inventory, which means that you look at all the inflows and outflows within the system that might generate emissions. Then in the life cycle impact assessment, you calculate the emissions and you quantify those. And then in the final interpretation step, you make your conclusions based on the assessment. As noted, we had 3 different scenarios that we were looking in this, or the alternatives. We had the plume stop alternative, the pump and treat with gap filtration, and pump and treat with foam fractioning. We will be further then referring to these with very short acronyms. So I hope that you take note that what the alternatives are. When doing the life cycle assessment and the greenhouse gas assessment, we took note that the site is located in UK. So we were using localized data for any production and use. And we had a cradle to grave approach for all of this. So taking all the production steps from creation of the materials to their final use or discard. And the reference time frame in this assessment for all alternatives was 15 years. Our baseline assumption was that most of the benefits will be achieved within this time frame. And the functional unit that what we were targeting to calculate was the tons of carbon dioxide equivalents generated during this whole 15 years time frame from cradle to grave for all of these alternatives. Then I'm going to show you quickly the system boundary and the scope of the assessment. So when we talk about cradle to grave framing, we start from the raw materials acquisition and end up in the end of life for those products. In the middle, there's everything from transport, manufacture of the products, transport to remediation site, any installation works, operations and maintenance during remediation, monitoring, and finally the end of life. For the colloidal activated carbon, what was included in the system boundary was first of all the plume stop product level LCA that we did separately. And to that we amended in the greenhouse gas assessment any transportation to the specific project site, any injection works that were needed, and any monitoring for the 15-year time frame for the project. It's worthwhile to know that there's no operation or maintenance in this alternative. As we move to the 2 other alternatives on the pump and treat, where first of all, the manufacturing of the equipment was included, manufacturing all the extraction wells, pumping wells, monitoring wells, transfer lines. The transport of all of those equipment to the site, most of them were manufactured and transported locally. Then the civil works needed for the installation, and then the continuous operation and maintenance for the 15 years time frame that the assessment was made to consider, including all the energy consumptions, the materials used, any maintenance work required, and also then the monitoring, and as end of life, the waste management, where the spent granular activated carbon plays a significant role. Looking into the life cycle inventory analysis, so this is where we quantify any materials used, any energies we use, any wastes we product, and any emissions that we create. Ramboll did a design for all the pump and treat equipment used within the remediation, and the basic design for the colloidal activated carbon installation was based on the real life installation that was introduced in the previous presentation. Well, then going deeper into the life cycle inventory analysis, This slide shows the key system variables between these alternatives. And if we look first and foremost for the colloidal activated carbon injection, here on the right, you can see the same diagram that was shown. The solution is based on a single injection round. Plume stop barrier is being created perpendicular to the groundwater flow. It consists of 102 injection points and 33 plus tons of colloidal activated carbon, the plume stop product. And for the injection works, other works, 1,600 liters of fuel is expected to be spent, and 3 monitoring wells are to be installed on site, and there will be a continuous monitoring for the 15 years, 2 times a year. Well, if we compare this then with the pump and treat alternative, again, a diagram shown on the right, this consists of a fixed equipment installation that are expected to be in a continuous operation for 15 years. 8 separate extraction wells are assumed to cover the whole groundwater flux zone. And likewise, as in the first alternative, 3 monitoring wells. There's a little bit more fuel consumption, 2,003 liters for the installation. Of course, the environmental footprint of the remediation equipment from the operation that was expected to be at 95% uptime with a constant groundwater pumping rate. And we were assuming 24 tons per year of granular activated carbon use and 64 megawatt hours a year electricity consumption. And in the addition to the environmental monitoring, which was assumed like for like with the colloidal activated carbon alternative, we were assuming 4 times a year operational and maintenance inspection from a nearby city. So then if we look at the third alternative, where in addition to the GAC filtration, we have a foam fractionation included, the key difference with that is being that we have reduced the activated carbon use to approximately 1/3, so to 8.5 tons a year. But at the same time, we've doubled the electricity consumption to the requirements in the foam energy requirements that the foam fractionation has. This is the simple diagram of the life cycle inventory scope that we had for both the pump and treat, and with the pump and treat with the foam fractionation add-on included. Then I want to touch a bit on one of the key variables in the assessment. Very early on in the assessment, it was noted that the granular activated carbon use is playing a significant role in the overall assessment. Based on the study that we did, there's a high variability in what kind of loading capacities or breakthrough times there are for long and short chain PFAS for different activated carbon types. But based on all the studies, the coal-based activated carbon is what most filter systems globally use, and they've shown very good results in the PFAS reductions. So the idea was that the pump and treat filters are this kind of packed flow through vessels, and they are operated in a lead-lag configuration. So this would minimize any breakthrough through the system. And if the foam fractionation step would be included, as in the alternative 3, then it was assumed that the activated carbon would only be used as a polishing step and as a risk management step. In general, spent activated carbon can be thermally reactivated, but there's no one really providing that service for PFAS, and hence it was assumed that the activated carbon is of virgin nature and it will be disposed to landfilling after use. So then a few statistics for those who are interested in dimensioning activated carbon or knowing more in depth about those. According to literature, the PFAS removal efficiencies for activated carbon are up to 99%, and The absorption capacity has a very high variability, as said, from 10 to 1000 milligrams per kilo. But this is always very much case specific. So depending on the water source, what is the PFAS specification, how much other TOC or DOC there is on the groundwater or co-contaminants, the absorption capacity can vary a lot. And also the typical filter empty bed contact times vary very much from 10 to 30 minutes. And the breakthrough, so how long it takes for the filter bed to be thoroughly absorbed and the contaminants to start leaching through, is from anywhere from 100 to 20,000 bed volumes treated. So in the right side table, you can see the figures that we decided to use on the assessment. And these are now in the low end of the variation range that was identified. We really wanted to be conservative in our assumptions in how much carbon would be used so that we wouldn't be overestimating that for the pump and treat systems. So for example, if the typical breakthrough according to literature occurs for pump and treat with carbon from everywhere from 100 to 20,000 bed volumes, we were using only 1,000 bed volumes as our basis. And from these figures, we come to the GAC use rate of 24 tons per year. Then we were also trying to identify any limitations that our study might have, and just going to highlight a few of the high and medium level concerns that were noted. The high ones are especially in the use of the activated carbon, whether it is for the pump and treat or for the colloidal activated carbon injections. These are always case specific. Even for the colloidal activated carbon, there isn't many references sites with 15 plus years of monitoring data to be used as statistics. Then a few of the medium level assumptions and limitations that I could flag. One of the interesting things that we noted is that, for example, laboratory analysis, we don't have any information about the environmental footprint of those. So assuming a site remediation where samples will be taken for 15 years, the total sample amount can amass to anything up to 1,000 plus assessment. And if those will be then sent with an airplane across Europe, that will have its own impact likewise. So now that we've collected all the data from the life cycle inventory, we started doing the life cycle impact assessment. And we do this as looking at the global warming potential and quantify that as the carbon dioxide equivalents. This means that we put all the different greenhouse gases that come, whether they're carbon dioxide or methane or nitrous oxides, we quantify those as CO2 equivalents. And there we have different global warming potential factors that are used to scale those different co-greenhouse gases. We did the calculations with an LCA tool, Gabi, provided by Sfera. Next, we will then move to the results. So, for the three alternatives, total for the 15 years operations, how many metric tons of CO2 equivalent were generated is shown on this graph. And as you can see, plume stop has a very small carbon footprint compared to the pump and treat with the granular activated carbon or with foam fractionation. This diagram separates the emissions to the remediation equipment, civil works, the remediation and operation stage, maintenance, monitoring, and waste management. As you can see, for the pump and treat alternatives, as also with the plume stop, the most significant environmental impacts in terms of the carbon footprint come from the remediation and operations. That includes any consumables like the plume stop or granular activated carbon use or the electricity. The other significant category is the waste management that includes any off-site treatment of these hazardous wastes, like the spent GAC, the PFAS foam, or the wastewater from the pump and treat effluents. All the other categories in this scale seem quite minor, but if we look at these in a table format in a bit more detail, we can notice that even thought, whether we're using in the operations phase direct injection of colloidal activated carbon or using granular activated carbon in the filtration step, there is a significant difference. But already when we are introducing a remediation system that has equipment built and installed on stage, those have a significant environmental footprint. Likewise, the electricity needed for operating them, the maintenance, and other aspects. And always when we have an alternative where we have some ex situ hazardous waste that we need to dispose or treat, we have to take into account the environmental footprint from those as well. So even thought the materials that we use for the remediation have a significant environmental footprint, also everything that happens before we start the remediation, and then at the lower in the value chain of the remediation side. Well, as the figures are very large, and we noted that we want to do some sensitivity analysis, especially in terms of the GAC use. So we made an assessment looking into what if we would assume that the carbon use would be at the low end of all the values that we found from the literature, or then at the high end of all the values. And we came into this kind of a range with the GAC use. So that would mean that the total carbon footprint of the pump and treat with activated carbon, for example, could be anything from 1,400 metric tons to 7,000 metric tons. Still significantly higher than with the plume stop, but possibly the difference would be much more marginal in comparison with the foam fractionation if both values for the GAC use were at the low end. Well, then about carbon handprint assessment. Carbon handprint is a way of comparing the potential carbon emissions or CO2 equivalent emission savings while comparing one method to another. So you always have a baseline method, and as the baseline method, we were using the pump and treat with granular activated carbon, and comparing that against the immobilization or with the pump and treat with foam fractionation. We can see that if we use the in situ immobilization, the plume stop alternative, instead of having a pump and treat with GAC, we are saving 3,867 tons of carbon emissions. Or if we are using that instead of the foam pump and treat with foam fractionation, we're saving over 2,000 tons of CO2 equivalent emissions. If we are using the pump and treat with foam fractionation and comparing that against the pump and treat with GAC filtration, we're also saving 1,700 tons of CO2 equivalent emissions. So finding a more environmental alternative in terms of the carbon footprint can help you generate a significant carbon handprint for your product, for your project. So a few conclusions. The results are case and site specific, and we had to do some assumptions in setting the stage. There's a clear impact that we can identify based on this assessment. And those are that the immobilization with the colloidal activated carbon had a 40 to 60 times smaller carbon footprint for PFAS remediation in CO2 equivalent emissions compared to the pump and treat based remediation alternatives. This is 1 to 2 orders of magnitude, so it's a very significant difference. So big that it really precludes any significant changes to the result, even though we do any adjustments to the assumptions and uncertainties. The biggest stages having the largest individual impact, the carbon footprint, were with the remediation operation, ranging from 70 to 80%, and with the waste management, with an impact from 20 to 30%. And it's worthwhile to note that the most significant life cycle inventory factor affecting the carbon footprint was related to the activated carbon use in all 3 remediation methods. The carbon footprint, say the break even for the plume stop alternative over the pump and treat based alternatives, occurs already after 2.1 months of operation. So for the similar carbon footprint, you could do a reinstallation of this kind of a colloidal activated carbon every 2.5 months. Well, then I will move quickly to the life cycle cost assessment before moving to the sustainability assessment. The life cycle cost assessment is a way to compare alternatives on a monetary terms. In our assessment, we were using the net present value as the metric. The net present value included in our assessment the initial capex for all the remediation and equipment and civil works, the future operating expenditure, there was any material inputs, any operations, maintenance, monitoring, or waste management costs. And we didn't calculate any residual value for any of the equipment. So, for example, the pump and treat equipment might have some value in the secondary use, so very minimal after the 15-year time frame. And the study period was similar to the greenhouse gas assessment. It was 15 years. And as we are using this kind of a net present value calculation, we need a discount rate to discount all the future costs to present day value. And we were using a 3% discount rate. And if we look at the cost breakdown in net present value for the 15 years of operation, the most significant costs for all of these originate from the remediation and equipment. So this includes all the colloidal activated carbon material, its application, the pump and treat equipment, and so forth. But if we look at where the differences then come between the alternatives, especially for the pump and treat with activated carbon and foam fractionation, we can see that for the pump and treat alternatives, there are significant costs in the operation phase included to any replacements, the operations, maintenance, monitoring, and the waste management. So this comes from the annual replacements of the granular activated carbon, 4 times a year site visits, changing of the pumps, fixing of the vessels, and the waste management of both the granular activated carbon, the separated PFAS foam, and the wastewater that's discharged from the system. Again, if we look at this in a table format, we can see that even though the equipment and the installation costs are quite similar, ranging from 1.2 to 1.8 million euros, there are significantly higher civil work costs for the pump and treat alternatives as they need fixed installations, and also for the replacements, O&M monitoring, and so forth. So if we look at the unit costs that is shown on the bottom, per euros there should be a cubic meter, not a square meter treated. But for the colloidal activated carbon, in this assumption, it's 2 euros per cubic meter treated, whereas for the pump and treat with granular activated carbon, it's 4.9 and for the pump and treat with foam fractionation, it was assumed to be 5.7 euros per cubic meter. And for those who are not, who want to see also the undiscounted value, not only the net present value, on the bottom line we show also the total cost of ownership in an undiscounted value. So we're not discounting the future monies to net present value. So in that alternative, the difference seems even larger, as most of the investments come already at an early stage for all of these alternatives. So whereas the undiscounted value for the in situ colloidal activated carbon would be in 1.5 million euros, it would be for pump and treat 5.7, and for pump and treat with foam fractionation 6.2 million euros. So the conclusions: the immobilization with colloidal activated carbon had 60 to 65% smaller total cost of ownership in terms of net present value. The largest differences in the total cost of ownership, they come from the capital expenditure, from the installation of the system, replacements of granular activated carbon, use of electricity, operation, maintenance, monitoring, and waste management. And if we look at the break-even, the financial break-even in terms of total cost of ownership for immobilization with colloidal activated carbon, that's immediate in comparison to the pump and treat based remediation systems. And if we look at the financial flexibility, a complete reapplication of the colloidal activated carbon could be conducted every 4 to 5 years, and still this alternative would have a lower total cost of ownership than the pump and treat based methods. Well, then briefly, I'll still run through a sustainability assessment before going to conclusions. The sustainability assessment was done with a sustainability assessment tool called Sure by Ramboll. It's a tool that's been designed for landowners, consultants, contractors, basically anyone working with contaminated land remediation. The aim is to support the remedial decision-making process and help site owners review any sustainability issues and convey and communicate those to other stakeholders. This is based on ISO Sustainability Remediation Standard, and it's also compliant, for example, the SURF UK Sustainable Remediation Guidance. We have been using this in about 1,000 projects worldwide, and just a few months ago it won the ESG Innovation Award in the annual Environmental Analysts Awards. And by the way, this is free online for anyone if you want to go try and out it. So the sustainability assessment for this case was done by a roundtable assessment with 3 Ramboll remediation professionals and further commented by region assist. We had 15 indicators from both environmental, economic, and social domains, and we did a semi-quantitative framing of those indicators on a scale of 1 to 5, reflecting the best option being 5 and then the worst option being 1. And likewise, we weighted all of those indicators on scale 1 to 5, describing the relative importance of those. The indicators that we used in the environmental, social, and economic domains were focusing on the greenhouse gases, water, natural resources. But on the society side, we were looking more at the long-term risk management aspects, the ethics of remediation, how it impacts the built environment now and in the future, and how it then helps communicating and managing the uncertainty to the future. And in the economic side, we were of course founding a lot of the assessment on the life cycle cost assessment, but also looking at things like the job creation, new skills generation, flexibility, and so forth. And if we look at the results, this graph shows the total sustainability assessment score. In this assessment, the score of 100 reflects an ideal remediation alternative. So it would be number 5 on this assessment on all of the scores and domains. And then everything 0 would be then the lowest possible score. And as we can see, the immobilization with colloidal activated carbon reached a total score of 83, mainly driven by environmental and economic indicators. If we look a little bit more in detail where those differences came, so especially in the environmental domain, the immobilization with colloidal activated carbon had clear benefits due to low greenhouse gas emissions, minimal energy and material footprint. In the societal side, immobilization with GAC had clear benefits from supporting the polluter pays principle and thus minimizing also the impacts on the built environment and so forth. And on the economic side, as we went through, it had the colloidal activated carbon alternative benefits from a very low total cost of ownership. So conclusions from the sustainability assessment: the immobilization with colloidal activated carbon had a 100% higher sustainability assessment score compared to the pump and treat based remediation alternatives. And the most significant impact in terms of sustainability was that the colloidal activated carbon remedial alternative superseded the pump and treat based alternatives, especially in the environmental economic sustainability. And that was specifically due to the low greenhouse gas emissions, minimal energy and material footprint, and then the low total cost of ownership and high financial flexibility. Then if we look at the pump and treat, whether with activated carbon or added with foam fractionation, the sustainability benefits came through the reduction of residual PFAS in the subsoil and from low perceived technological uncertainty with having a technology that's been applied often. And also the pump and treat, as it is a bit more labor intensive remediation method, it benefits the local employment more due to extensive installation and constant OM work required. So then just a few conclusions and key findings. To sum up, based on the life cycle assessment, life cycle cost assessment, and the sustainability assessment, the immobilization with colloidal activated carbon had 40 to 70 times smaller carbon footprint in CO2 equivalent emissions. It had 95% plus smaller raw material, energy, and waste footprint, and 60 to 65% smaller total life cycle costs compared in net present value. And then also viewed on the more semi-quantitative multi-criteria analysis for the sustainability assessment, also including the social sides, the colloidal activated carbon had 100% higher sustainability score compared to the alternatives. And then just a few additional notes. When doing site remediation, you should always consider sustainability, and that allows you to understand that the remediation is not happening in isolation. All the actions that we do to reduce the contamination levels, they have impact somewhere else in the society or in the environment or in the economy. So take a balanced and a holistic approaches for this. In our example, the environmental benefits from the colloidal activated carbon technology are immediate. And for example, the reductions in the climate impacts, if those can be achieved now, that is very important looking into the phase of the climate greenhouse gas emissions that are being currently generated and the climate impacts that is having. If we look at this kind of a novel innovative technologies like the colloidal activated carbon it has also a potential for introducing significant carbon handprint for the project in comparison to other alternatives. And the product itself has an opportunity of negating climate emissions through long-term carbon sequestrations back to the soil. And in every project, I want to highlight that there is some simple ways of reducing the negative sustainability impacts. And these are very simple tools, such as using biogenic waste materials, for example, for activated carbon production, reducing any offsite waste treatment, trying to increase circularity for projects, and using, for example, electricity from renewable sources, preferably sourced on-site. With these words, I want to thank you very much for listening to the presentation on the sustainability impacts on this case. Thank you.
All right, thank you, Jarno. That concludes the formal section of our presentation. So at this point, we'd like to shift into the question and answer portion of the webcast. Before we do this, we want to acknowledge that we are running over the hour for this webinar. We don't want to cut short any of this really valuable information, so thanks to those of you who are staying with us. And if you do have to hop off, we will be sending out a link to the recording after the webinar. Also, you will receive a follow-up email with a brief survey. We really appreciate your feedback, so please take a minute to let us know how we did. All right, so let's circle back to the questions. Here is a question for Jarno, and the question is, did you use an existing life cycle analysis or environmental product declaration for the granular activated carbon used in the pump and treat and for the plume stop?
No, not completely. For biogenic material-based granular activated carbon, there is not a ready data set. But when we were doing the LCA work, we amended the existing database data, that is with information from scientific literature. So it was an add-on with both the existing database data in the GABI's data sets with data from scientific literature.
Okay, there's another question here, and it is, are there any further climate change or carbon sequestration ramifications in the in situ plume stop approach that are not covered in this study?
I shortly noted about the carbon sequestration. So that is a very interesting additional benefit that the plume stop alternative has. So when the plume stop is an activated carbon-based product and it's injected onto the soil, onto the subsurface, it acts there simultaneously as a biochar. And what biochar does is that it binds carbon from the atmosphere and puts it into the soil, where it's stored for long term, while also increasing the ecosystem services potential that the soil has. So there are multifaceted benefits from this kind of a technology, but again, that's one additional stream, the discussion of sustainability, and we didn't want to add it already on a lengthy presentation.
Okay, thank you, Jarno. Somebody is asking about social sustainability. How did you assess this as part of your sustainability assessment?
That's a very good question, and that's a very difficult field. It's much more easy to quantify, for example, carbon emissions when we can calculate those based on data. But when we go to the social side, it's more about stakeholder engagement. So that's why in this project, we had a roundtable of 3 Ramboll professionals, and then we had a dialogue with also the Regenesis professionals, trying to really drill down into the different sustainability aspects and trying to go into the local site owners or inhabitants perspective. Of course, we cannot do that perfectly, but we aimed to do it with this kind of an roundtable approach.
There are some questions about the plume stop approach here. So the first question regarding the plume stop approach is the PFAS just contained in the barrier without degrading, and will it not eventually break through?
So yes, it is about sorption without degradation. What we're doing is looking at retaining the contamination in the subsurface so that it reduces the impact on the down gradient or prevents any impact on the down gradient receptor. If the challenge concentration continues at the same level, then eventually you will get breakthrough. Now, this might be decades down the line. Essentially, you've got contamination, you've got competitive absorption between the contaminants through the barrier, you get rollover of the contaminants through the barrier, and eventually it will break through. Now, in a situation where you don't deal with the source, what this might mean is in 20, 30, 50 years, whatever it is, you would come back and reinstall another barrier at that point, and then you'd get the same time again. But ideally, what you'd be doing is something that I mentioned on this site, which is you'll be reducing the source as well, either removing it or stabilizing it, preventing the leachability from it. And what that does is it reduces the challenge concentration coming into the barrier, so the barrier lasts even longer and potentially doesn't need to be replaced.
Okay, so here's another question, and it is there a potential for the plume stop product to migrate away from where it is injected?
Well, it's designed to do that to a certain extent. So if you look at the two products we'll be using for PFAS, we've got Source Stop and Plume Stop. Source Stop is not designed to move so far through the formation because you're probably using it in the source area, close injection grid. Down gradient in a plume, we want the product to move so that we can reduce the number of injection points, and that keeps the project cost effective. Of course, you don't want the product to then wash away. So the idea is that the product moves through the formation, and as it moves, it's slightly negatively charged. And then the first mechanism is that it will attach to positively charged compounds on the aquifer surface. And then the polymers that are carrying the colloids of activated carbon, they will break down very rapidly through biological degradation, and the remaining colloids will then just settle out. So you then coat the aquifer at that point. So that'll all happen within a few meters of the injection point. If we think that it's a really fast flowing aquifer or it's a really clean sand, something like that, we can also use a parking agent as well, something like calcium chloride. And what that does is it breaks these polymers, and we can drop out the product where we want. So we can design the shape of the barrier itself, the dimensions of the barrier, so we get the sorption and the retention that we're aiming for.
Okay, there's another question here, and it is, are there any free tools available that can be used for calculating the carbon footprint for remediation?
I think I will take that. There are for different geographic regions. For example, in US, there is the Sitewise tool. Unfortunately, that's not really applicable in Europe. There's always some geographic variables that are included in the specific tools. And in Europe, there's also been a few initiatives and projects, but I think that those tools have not been kept up to date. And this is always a very much site and case specific with the assessment. So if you use a very simplified tool, you will be neglecting a lot of the key variables.
Okay, so another question here is, the cost analysis was for 15 years. Would this change if considered over a longer period?
I can take a stab at that. I don't know whether Janu might want to join in, but the idea of it being 15 years was, what we wanted to do was make this assessment as fair and as conservative as we could. So in modeling the barrier on this site, the shortest amount of time that we could consider that you might need to reapply was 15 years. So we picked that as a period at which you might come back and re-inject. Now, the reality, as I say, is we're probably going to go in and sort out the source area, so the challenge concentration will go down, so the life of the barrier will lengthen anyway. But if we took the worst case scenario that the barrier did need replacing after 15 years, then what you would do is you'd have to spend that million euros again at that point. Now, the pump and treat system would have cost, I think it was 3.75 million by that point, and then it would continue to do so. So for instance, we would reapply after 15 years. So by the time you get to the 30-year mark, it would have cost 2 million. With pump and treat, by the time you get to the 30-year mark, you'll have been on to something like 8 million, something like that. Now, the costs don't land at the same time. The pump and treat costs are spread out through that time, whereas with the plume stop, you're just getting every 15 years you'll get a cost. But essentially, you can look at those costs and say that they are linear and that they'll increase at these same rates over the time. Now, net present value sort of bends that curve a little bit, but essentially I think you can just take those numbers and extrapolate those forward. Does that make sense, Janu?
Yep, I think that was very well explained.
Thank you.
All right, so that is going to be the end of our chat questions. If we did not get to your question, someone will make an effort to follow up with you. If you would like to learn more about Ramboll, you can visit ramboll.com. If you would like to learn more about remediation solutions from Regenesis, please visit regenesis.com. Thanks again very much to Jarno Leitinen and Gareth Leonard, and thanks to everyone who could join us. Have a great day.